All right, I guess we're going. So welcome to our September community meeting. It's been a while since we had one of these. We've been working hard on our 0.10 release. So our last meeting was in June, and those YouTube videos are live. We have introducing the Pravega Flink connector video in Pravega with GStreamer, and a talk that'll be superseded by this community meeting, but we introduced the Presto query engine for Pravega last time. This time we'll be deep diving into that and have an update there. Just a couple quick community developments to highlight, and then we'll get right into today's presentation about Presto and Trino. But we held our first Chinese community meeting back in July. That's how we have a Chinese version of the Flink talk. The ZIO connector prototype has been released. So you can check that out on github/chelib/ZIO-Pravega. ZIO is similar to Akka in the Scala land. So, and Ashish Bhatwara recently presented on Pravega, GStreamer, and open source video analytics at NASCOM, which is a large conference in India. And last month or so, we introduced our approach to fault injection with Litmus Chaos. And we're working now on open sourcing that approach so that we can make what we're doing behind the scenes reproducible. And our 0.10 release cycle is underway, so check out Slack and follow that. And then today's agenda is this distributed analytics over stream storage, a technical deep dive into our Presto and Trino connectors. So you can check that out at github.com/presto/presto-connector. And I'm pretty excited for this. So why don't I stop sharing and you can take it away, Karan?
Sure, thanks, Derek. Let me share my screen here real quick. All right, so can you guys see my screen right now?
Yeah, that's good. Oh,
awesome.
There you go.
Awesome. So first of all, thank you so much for everyone for taking out the time and attending this presentation today. We won't be wasting any more time and diving straight deep into today's topic, which is distributed analytics over stream storage. We'll be diving deep into two flavors of a product, Presto and Trino, and how we have connected those with Pravega here. The presentation will be delivered by myself, Karan Singh, and my colleague here, Andrew Robertson. The topics that we'll be discussing today in this presentation we'll start with a brief overview about Pravega, moving on to defining some concepts and some jargon about Presto, followed by schema registry, which is one of the Pravega's project, which we use here as we build the connector for Pravega. Moving on to Pravega connector for Presto, which would be Andy would be taking over there, and defining splits, processing splits, and then talking a little bit about Trino, followed by a brief demo, and then moving on to the questions, if any, for today. So let's dive straight into it. All of us present here would be mostly aware about what Pravega is, but just to give a brief overview of Pravega. Pravega is nothing but a stream store. It defines stream as a storage primitive. The foundation of this is segments. What exactly are segments? They enable a flexible composition of streams and stream scaling in Pravega. Talking a bit more about streams, as we said earlier, that Pravega defines stream as a storage primitive. A stream is nothing but a storage abstraction for continuous and infinite data. Some of its properties are that it's named, it's durable, append only, and can support infinite sequence of bytes. It has a low latency, appends to and reads from the tail of the sequence. It has a high throughput reads for older portions of the sequence as well. Stream scaling, moving on to stream scaling. Streams basically in Pravega adapts to changes in incoming workload. It changes the number of segments dynamically to support for incoming new data. And it also respects order. So this was a little brief overview of Pravega. Now let's dive into what exactly is Presto. Something that I would like to an important note before we dive into Presto is that Presto and Trino are two different flavors of a very similar product. The reason why we start with Presto is because we started developing the Presto connector for Pravega first, and then we very recently in the past 2 weeks added support for Trino as well. So all the high-level concepts that we'll be talking about here would apply both for Presto and Trino. So just so that there is no confusion as we go ahead explaining about Presto and Trino. So what exactly is Presto? Presto is an open source distributed SQL query engine which supports fast interactive analytical queries. It has support for both non-relational as well as relational sources. For instance, it has support for MySQL, for MongoDB, for now for Pravega, and even for S3, which is an object store. One of the main things about Presto is that it queries data where it lives. So it essentially separates storage from compute. The compute need not happen at the level where the data is being stored, which is one of the interesting properties of Presto. It has the ability to combine data from multiple sources. It gives us the ability for data virtualization, which is nothing but we can query various formats of data, like I mentioned, relational, non-relation, and then perform joins amongst them, and moving on, performing certain analytical queries on varied sources of data as we process them from the same compute. Presto has become pretty famous over the years. It has gotten attention from companies like Facebook, Airbnb, Netflix, and now even we at Dell Technologies use it. Presto started in the year 2012 at Facebook, and then it was officially released as open source in the year 2013. This is a little bit about the scenes on the road of Presto, and moving on to the architecture of Presto. So talking about the architecture of Presto, the diagram that we refer to here is that we have a Presto client which issues queries. So this client is basically used to fire queries on coordinators, and then the workers are supposed to return the results to the client. The main architecture is such that Presto can support multiple workers, but has a single coordinator. The role of the coordinator is to take the query, which is fired from the client. It parses and analyzes the query, passes it to a planner, plans the entire query in stages and tasks, which we'll be talking about later on. Then it schedules the query, and then passes on query to a process on splits of data or certain sections of data, which is then done by the workers. The actual processing is done by the workers. The workers can scale out from any number from 1 to X, depending on the amount of data that we're trying to process and depending on the workload that we have. The coordinator of Presto refers to metadata APIs in order to parse and analyze the queries, and then uses certain data location APIs provided by the Presto code base to schedule the queries and pass it on to workers, so that eventually workers can work on the queries and return results back to the client. So this is the high-level architecture of Presto. Moving on to the topic of why Presto. Why did we choose Presto? Some of the main things that we already just talked about Presto is that it supports data virtualization, which is we can query disparate sources of data from the same compute and perform queries and joins on these sources of data, which is one of the most interesting factor here. It was pretty easy for us to have connectors for an object store and a stream store, and query data and join data coming from both these stores. So that's where Presto plays a huge role, and we can do this with any of the data sources as long as we have a connector for Presto. It supports a pipelined in-memory execution and is a classical MPP, which is nothing but massively parallel processing architecture that we just saw earlier. It has support for vectorized columnar processing, which is really important because it reduces the amount of data to be processed as compared to a row-based processing, and thus resulting in faster queries and faster results. We already talked about how it separates storage from compute. We did not process the data where it lives. We can process the data in the compute layer, and thus there is a difference between the storage and compute. It's written in highly tuned Java. It uses efficient in-memory data structures. It has very careful coding of inner loops and has bytecode generation. These are some of the main reasons why we wanted support for Presto and decided of building up Pravega connector for Presto. Let's talk a little about Presto jargon before we move on to the actual connector. So there are some of the terms defined by Presto which might be confusing, so we'll go over that here. One of the major things is the server types we talked about in the architecture. It has a coordinator, a single coordinator, and a worker which can scale from one to many. The main task for the coordinator is parse statements, plan queries, and manage the workers. And the workers are supposed to advertise themselves, execute tasks at the low level, and process the data. Actual processing of data is something that happens on the worker nodes. Talking about data sources, the way Presto defines it is in 4 things. Number 1, the connector, which we will talk about later, the Pravega connector. Similarly, Presto has multiple connectors. It has connectors like Elasticsearch, it has connectors like MySQL, MongoDB, and several other data sources, which it refers to as connectors. A connector is nothing but an implementation of a Presto SPI, of Presto's SPI to interact with the resource. Each connector then comes with a set of catalogs. We can have one catalog which contains schemas and references the data source via the connector. So this catalog will essentially contain then schemas, which is nothing but something that organizes tables. It defines a set of tables when combined with the catalog that it is a part of. And then we have the basic definition of table, which is same as any other table. It's a set of unordered rows organized into named columns with types. So these are the data sources definition in Presto. Now we'll move on to talk about the query execution model of Presto. So it has 4 major components. One is the statement, second is the query, third is the stage, fourth is the task. What's a statement? Statement is nothing but SQL compatible statements written, just pure statement, not the query. So the query when just written is referred to as statement in Presto. It just refers to the textual representation of an SQL statement. A query, the configuration and components instantiated after the statement is issued to Presto is what Presto refers to as a query. It encompasses stages, tasks, splits, connectors, and data sources, which we will talk about in the next slide. What is a stage? A stage in Presto is nothing but when the client issues a query, Presto breaks up a query execution into a hierarchy of stages, which are then executed in parallel by a series of tasks. So stage is the highest level of abstraction for tasks. And these hierarchy of stages that comprises a query can be resembled something similar to a tree, where the root stage is responsible for aggregating the output from the other stages, or talking about the analogy, the other nodes that are present in the tree as child nodes of the root node. And the coordinator uses this stage to model a distributed query plan as it prepares a plan for the workers, which will process the data on the worker nodes. But the stages, one important point to note here is that the stages themselves do not run on workers. Stages are something that's only used by a coordinator to model a distributed query plan and giving it out to the workers. The next level of unit after stages for a query is a task in Presto. Each stage is implemented as a series of tasks which are distributed over a network of Presto workers, and these tasks are assigned by this stage is set up by the coordinator and assigned to the workers as tasks. Workhorse is a term that Presto uses in the architecture as a distributed query plan is deconstructed at the worker level into a series of stages, translated to tasks and processes which are executed on the worker nodes on snaps of data or splits of data. It executes in parallel by a series of drivers. So the next unit after task that comes into picture for Presto is drivers. Before talking about drivers, we'll talk about split. So these splits are nothing but these splits are nothing but little parts of the data that we define. These splits are defined by every connector. It basically breaks the data into smaller version of that data and then given it to specific workers so that those splits are processed by the workers on the worker nodes and then aggregated together when multiple workers work in parallel on the splits that are given to them, assigned to them by the coordinator. The task operates on these splits, which are nothing but sections of a larger data set, like we said right now. When scheduling a query, a coordinator will query a connector for list of all splits available for a table. The coordinator is the guy who is responsible for keeping track of which worker nodes, which machines are running, which tasks, and what splits are being processed at the worker nodes by individual tasks. So this is the job of the coordinator. Moving on to talking about the driver, which is the next unit of worker unit of task. So a driver is nothing but a sequence of operator instances or a physical set of operators in memory. Like we said, it's an in-memory execution. Presto follows that model. It can be said to be the lowest level of parallelism in Presto. Each task, as stages are defined in tasks, and each task will contain one or more parallel drivers, which will then combine operators to produce output that is aggregated by a task. And this output aggregated by a task is then delivered to another task in another stage. So we have stages, we have tasks, and we have drivers. Now, talking about the operator, operator is the basic definition of a general operator that would work anywhere in a database world. It consumes and transforms and produces data. A table scan fetches data from a connector. It produces data that can be consumed by other operators. And similarly, one example is that a filter operator consumes data and filters, that is, produces a subset by applying a specific predicate, which is specified in the query over the input data, where the input data can be a small section of a larger data set that is a split. And then the filter operator basically applies a predicate over that input data on a particular worker node where it is running or being processed. What is the term exchange in Presto? The transfer of data between Presto nodes that happens is referred to as exchange. We talked about this earlier when we said that the operators deliver tasks to another stages. This entire process is termed as exchange in Presto. Different stages for a query, there are different exchanges happening while the data is being processed. A task produces data into an output buffer, and it is consumed from other tasks using an exchange client. So whenever data is required during aggregation or anything, while we need data from other workers, while processing is happening on the worker nodes, the exchange client is used to basically consume data from other tasks and exchange data between such tasks. Now we'll be moving on to Pravega schema registry, which Andy will be explaining from here on, moving on to talking about a little bit more about the actual connector of Pravega. So Andy, it's all yours.
Okay, thanks. Just want to show this. Can you show this whole slide? Does it come up one by one? Yeah, I'll be a little easier. Yeah, Karan will stay driving, so I'm going to pass it back to him. Schema registry, right? So there's a, I'm sure most everybody knows that there is a Pravega project called Schema Registry. And we're pretty well integrated with that. We'll use it if it's available. It provides some nice features. So as you might imagine that you need some sort of schema in order to be able to query from a Pravega stream. You can't just have data in a Pravega stream right now and just arbitrarily query it, right? So having a schema tells us what the field definitions are and how the object is made up so that we can get what we need out of it, right? And so that's when Presto is going to ask us what the table definitions are. We're going to look up the schema and we're going to give it back to Presto. So when we're getting metadata for Presto, we're going to build a list of schemas and tables, right? That's what Presto is interested in. And then for us, for Pravega, schemas are Pravega scopes and tables are Pravega streams. Okay, so when you list schemas, we're listing scopes, and when you list tables within a schema, we're listing streams within a scope. And then when it comes time to actually get a schema for a particular table within a schema, we're going to go someplace to get that. And that will either be schema registry, the Pravega schema registry product that's running, or we're going to look in a known location on disk for a user-defined file. And I'm going to show both of these things in the demo, which I think it'll make it a little bit more clear. But again, just to call it out, a Pravega scope and stream is equal to a Presto schema and table. Can you go next? So again, I'm going to show an example of this. So I don't have to go too much in detail, but basically we're just defining what the schema and table is. The object name is the stream name. What the fields contains in that table are, their formats, the data format, in this case CSV, and then that's going to map to some table definition in Presto. Okay, next. So when we're actually looking at the points, so a lot of what Karan went on is pure core Presto stuff, which doesn't necessarily involve us too much. But the SPI that he mentioned basically is broken down into these three areas, right? So there's the metadata API, which is, a user is going to type something on a CLI or send a query, and Presto is going to ask us, okay, what schema names are within your catalog, right? In your connector, and we're going to give that to them. Again, in our case, that's the scopes that are in Pravega. Get table handles and list tables. That's going to be finding out what those tables are, right? So those are streams within a scope. And then get column handles and get table definitions and things like that. That's when we're actually going to go look up a schema for the particular scope and stream, right? And again, that's either looking at schema registry or some locally defined schema. The next kind of core component is driven again by the coordinator, and what the coordinator is going to do is, at this point the user submitted a query. It's done a bit of planning, and now Presto is going to say, okay, here's the data the user has requested. Here's the fields and columns involved in the query. You give us a list of splits that we can run to satisfy this query, right? So a list of split, we're going to go and figure out what that is. We'll have more detail later. We're going to give it back to a coordinator, and basically that's the set of work that needs to be done to satisfy the query. And each split is one discrete piece of processing that can be given to a worker, right? And then we're all taken together. You get the results of your query, right? So that's another thing that Presto is going to ask for. And then there's the actual processing that's going to happen, and that's going to happen on each worker for each split. So Presto is going to assign a task, which is a split, and the worker is going to run it, and it's going to ask us for data, and that just includes things like actually fetching the data for a row or an event, and returning data of values for a field when Presto asks for it. So these are the three more main areas. Next. Okay, so defining splits. What you, and generally in Presto, right, you don't want, there may be hundreds of workers available on a Presto cluster, right? I think the default is 100 workers per node, right? So there's a lot of different threads that are available for handling work. So ideally, you would be able to split the work up such that things are maybe spread out evenly, or at least you're not doing a lot of work on just like a small number of threads, right? When you have a lot of processing power available, right? So, and we'll touch on this later. So what's available now and what can be available and soon in the future are a bit different, but I'll talk about kind of how things are now and a little bit of things in general, and then kind of get into where we're going. So right now, out of the box, there's one Presto split per segment within a stream, right? So when the time comes for the coordinator to ask us what the splits are, we're going to, using the Bash client API, figure out what the segments for the stream are and assign those and create splits from them, right? So, and again, as many of you know, right, this is controlled by like the scaling policy. So if you have 100 segments, right, that's going to result in 100 splits, right? And I'm sure, You can also figure out that if there's only one segment that you only have one split, right, which is maybe not ideal. That brings us to the next point, which are stream cuts, right? And these are, a stream cut is a position of all segments within a stream, right? So it notes a position across all the segments in a stream. So with this, you can kind of get start and end boundaries, right? So with this, we can kind of cut things up, right? So if we have known stream cuts within a stream, right, instead of one split per segment, it becomes you know, the number of segments times the number of stream cuts, right? Because we're going to have one for each of those. Next. So what we have now is user is able, and a user application is able to keep an out of band mechanism for telling us what stream cuts within a stream may be, right? And in this case, we're looking for just a specially known stream. If it exists, we use it. If it doesn't, we don't use it, right? And again, this is out of band, and this obviously has limitations in it. But if it's there, we'll go and we'll figure out the stream cuts from there, and then be able to split things up a little bit more fine grained. Next. There's some pseudocode which I have to go over too in detail, right? But basically, the idea is a user application can write to this specially known stream, and every so often persist the stream cut, right? So maybe this is based on number of events, or maybe it's some size of megabytes, right? Maybe they figured out that if a split is 32 megabytes, that's a good size for processing in a split. You can create a stream cut every 32 megabytes, and we'll be able to create splits of that size. Next. Okay, so again, I'll touch more on like the future work that makes all that a little bit more seamless and more user friendly. So processing splits. So this is actually the work that the core work that the connector is doing to get the data. So the splits are defined, and then they're sent out to the workers, right? So a worker is going to be assigned a split, and in our case, that split's going to be assigned, that's going to be mapped to a specific segment range, right? So we're going to be looking at a segment range of one specific segment within a stream. And that's what that split is responsible for returning data from. So at the high level, it's going to read raw event bytes from the stream for every event in the range. It's going to produce some object, right? And this is basically a list of the formats that we support, so protobuf, Avro, JSON, and CSV. It's going to set up field value providers to actually get values from the object. And then we're just going to give values back when asked by Presto. Right, so that's the high level. And as Karan mentioned earlier, right, it's all columnar, right? So Presto is basically building pages of data. So the components involved in this are row decoders, which is a collection of column decoders. And there's one for each field and column involved in the query. And the column decoder is basically setting up this thing called a field value provider. And that's all about how do I get this value for a given field, right? So if you have a JSON and you have a field within that, within the schema that's like address / street, right? It's going to set up field provider that knows how to go into your JSON object and get the value when asked for it. And then at that point, Presto can get the value, right? Presto knows what the type is and will come and say, okay, for this given field, get me a Boolean or get me a log, right? And we'll convert it and give it back to you. Next. Okay, so now we have to turn raw events into rows, right? So we just have these arbitrary events and data in Pravega, and we're gonna actually turn it into something usable in a row. So there's two kind of ways that data may have been written into a stream, right? So data could have been written using a serializer provided by schema registry. And then there's a schema registry unaware client, right? So these are kind of like the two basic things, right? And we have to handle these things a little bit differently. And I'll go over this in the demo and actually show a little bit of code to help clear this up. So if data was written with the schema registry serializers, we need to create a schema registry based serializer. And the reason for that is when the event data is written to Pravega, there's a little bit of encoding info that is persistent along with the events that's written inline to the event. And that lets the schema registry deserializer figure out what the schema is and produce an object back to you, right? If we don't have this, then we're going to have like a malformed object because that encoding info doesn't mean anything to us. We don't know how to interpret that. And then there's the other way, which is schema registry unaware clients. And then in that case, we have to create our own deserializers, which are going to produce an object for us, right? So in this first case, we use schema registry serializers, and it just gives us back an object. And in the other case, we actually have to take the schema, figure out how to parse it into a readable object, and we do that on our own using the schema that the user provided. But the end result is a deserializer that can turn an event into an object. Next. So continuing this, the main kind of driver is a record cursor. So this is what Presto is going to have a handle to, is a record cursor for a split. And this is the thing that's like, okay, fetch the next row and then give me data for this field within this row. So when you open a record cursor in our implementation, this is basically going to map to opening a segment iterator for the segment range, right? So we're actually, so we're using the Bash client API. So we're just dealing with raw byte buffers here. And then when asked by Presto, right, we're basically just reading the next event buffer, right? So we're just getting the next segment or the next byte buffer from the iterator. We deserialize it, right, using either either schema registry serializer or not. And then we're building the row decoder that we talked about, right, which is how do we get values out of these fields. And then Presto may or may not ask us for values for any of those fields. But if they do, it'll look something like get long, here's the field, and we look up the field value provider for that field and we return a long. Why I say they may or may not ask us is not every field that we end up getting may be involved in the query, right? We're not just returning all the data. You may be doing something like select count star from table, in which case the values really aren't read at all, right? So it kind of lazily gets data from you when it needs it. Okay, next. Yeah, so future work, right? So I mentioned the defining of splits, right? And take the case where you have one segment. Let's say you have one segment for a stream, and it's many gigabytes worth of data, right? Obviously, that's not ideal for processing it if you don't have any stream cuts. So we do have still in POC, we have work where we can use some internal Pravega metadata about a stream to do that for us, right? So again, as probably a lot of you are aware, there's the idea of watermarking, and we can use this information to then define splits of an arbitrary size, right? So you would be able to say, I want a split of 64 megabytes, and we'd be able to then do that. There's no out-of-band stream that you need to maintain or any of that kind of hacky stuff, to be frank, or anything like that. So it's all kind of seamless to the user, and that this is coming. Next. All right, I'll pass it back to Karan.
Thank you, Andy. So we now talk a little bit about Trino. Like I mentioned earlier, Presto and Trino are nothing but two different flavors of the exact same effort that started at Facebook in the year 2013. The main reason why this effort was started because Facebook was unable to query close to 300 petabytes of data using Hive, and they thought that Hive was pretty slow as compared to the response time that they were expecting for this data. And that's where this effort started of building something like this, that we have two different flavors right now of Presto and Trino. This is a brief timeline which clears things of what exactly is Presto and Trino. And one important thing to note here is that there are two open source tracks, Presto and Trino, like we said earlier, and we do have support for both of them. Pravega has support for both Presto open source track as well as the Trino open source track. The only reason we mentioned Presto during the presentation while explaining the concepts was because we started developing with Presto earlier, and we just added support for open source Trino just a couple of weeks back. And thus the demo will also be based on Presto, since it was something that we had from earlier. So, but we do have support for both the things. So if the users want to use Trino or Presto, we do have support for both of them in Pravega. Moving on to talking about Trino and Presto. So like I said, both commonly was applied to replace Hive as a data lake query engine at Facebook, and federating queries across multiple data sources by separating storage from compute and supporting data virtualization. Some of the things here mentioned under Trino and Presto are future work or current work that or efforts that are advancing both the projects. For instance, Trino has now support for high precision timestamp, which is useful for in the domains of fintech, gaming, and other industries where like high granular time support is necessary and required. It also has support for advanced SQL capabilities like the Windows syntax and pattern matching on Windows through the match recognize construct of a query. It supports dynamic filtering and dynamic partition pruning support that removes redundant scans by cluing in the optimizer on which partitions need to be included in a query join whenever we fire a query which has any join. So it has Trino has support for that now. Some of the future projects that are being worked on or currently in the beta version in Presto is these projects, Project Aria, which has the ability to push down expressions to a data source for specific file formats like ORC. They have proposed project Presto Unlimited, which is to introduce exchange materialization for creating temporary in-memory bucketed tables so that it decreases the overall memory footprint when Presto/Trino executes a query. So this is one effort from the Presto side. Similarly, there are multiple efforts like supporting dynamic SQL functions. Presto and Spark is something that was recently introduced on the Presto side. It runs Presto code as a library within the Spark executor. There has been ongoing efforts in supporting disaggregated coordinator, which is basically scaling out the coordinator horizontally and revamping the RPC stack. Right now, Presto and Trino support only a single coordinator and multiple workers. So there is some efforts on this area as well. Then there is a RaptorX project, which is 10x faster Presto with multiple level caching. So these are some efforts coming straight from the communities of Presto and Trino specifically currently in these projects. Now we'll be moving on to a quick demo by Andy, which is based out of Presto, but just to put it again, the exact same thing can be done with the Trino support for our Pravega as well. Andy, would you like to share your screen now?
Yes, one second. Okay, can everybody see my screen?
Yep.
Okay, so also on the GitHub, there's a little getting started guide which will show how to do this. And I'll just go over this quickly to show you what it entails. So we're basically going to bring up a Pravega stack, including schema registry, and we're going to bring up Presto Docker image as well. So just, I mean, this is just a list of steps. I only wanted to go over one or two things. The first one is we actually have to build an image with our plugin in it. If you look at Presto, DB, and Trino code bases, basically all their connectors are in the respective mainline repositories, right? So when they build an image, it's all the code's there. And we, for the moment, have not done that. We basically just have our code in our own repository. So we're just basically producing a plugin tarball that then can be loaded into an existing system. It doesn't preclude us from eventually merging somewhere else. It's kind of the way we have it set up right now. So we do have to build an image that it contains our code. So if you're running this, that's one of the first thing to do. You're just going to Docker compose everything up. And then you can actually run a demo. And the demo is basically just inserting some test data. And then you're able to query it, right? And it's going to write data in 3 different ways, which explains kind of the 3 different scenarios that we're going to see in the connector. And I'm going to show a little bit of the code that explains that. So I have already just done this. So I Docker composed all the services up. It's all running. I ran the demo. I ran event. It inserted 1,000 sample events for each type. And you can see that there's going to be 3. So I have a demo.inventory, and that's Avro, and this is the schema. Demo.sensor, it's JSON. Here's the schema. It wrote a few events, and then this thing called demo transactions, and you'll note that there's no schema shown, and we'll talk a little bit about that in a bit. This is the code app. This is the little client app it's in that code, and this just basically just inserts that test data, and it calls out the 3 different cases, right? So the first case is it's writing using serializers provided by schema registry, right? So we're creating this serializer using schema registry, and basically when we write an event, it takes care of persisting that schema to schema registry for us. And then likewise in your client app, when you read it out, it'll just give you an object. You don't have to actually get your hands dirty with the schema, right? And this is on the inline sort of way. Second case is you're using schema registry, but you're managing yourself, right? So you say, okay, you're explicitly adding the schema to schema registry, right? But you're just using some serializer that of your own, right? To schema registry unaware serializer, right? But the schema is still there in schema registry. And then the third case is you're just writing the data yourself and you haven't put the schema anywhere, right? So there's no schema registry anywhere involved in this. You're just using some regular serializer, right? So these 3 cases are the 3 streams that were written. In that last case, this maps to there, so demo.transactions. So this is how you can then tell, if you're not using schema registry, this is how you can tell the Pravega plugin what the structure of your data in your stream is, right? So if I look at this transactions object, right, you can see that I've just mirrored the schema here, right? So you're saying, this is the scope name. Here's the stream name, which are going to be the schema and table names. It's in JSON, and here are my field names. Here's their types, right? So now this is what what the connector is going to look at when getting metadata for this table, right? And then this is also how we're going to be able to parse out the values from your object later, right? So you don't have to use schema registry if you don't want to, even though it does provide nice features and things. You can just provide schema locally. And this schema file is included in the Presto image so that the coordinator has access to it. So I'm going to go ahead and just open a shell to Presto, right? So this is basically just running Presto CLI that's, right, so you can see that it built, this is why we just have in the name our image, Presto with Pravega, right? So now we have a shell, right, to Presto CSI. CLI, so you can show catalogs, and again, these are the different data sources that are available. There's some built-in ones, and you can see Pravega there. And so show schemas from Pravega. So what this is doing now is going ahead and listing scopes from Pravega, right? There's just one. I said it was demo. Now I'm showing tables, right? So now it's going and it's listing streams within the demo scope in Pravega, and you see these 3 here, right? So at this point, all we've done is just query from Pravega. We haven't done anything with schema registry yet. So inventory was the first one. You can do things like describe inventory. So at this point, we're going and checking to see if there's something in schema registry that has this name, and it does. So product ID, quantity, and origin source, which are just probably don't mean anything, but they're there. Same thing for sensor. And then transactions, right? So these first two went to schema registry and found the schema, and this last one, it was found locally. So that's what we used. So where to look in schema registry. So we do require a specifically named group, or we have a format that we're expecting, right? So that's just simply scope that stream name. So when you create a group within schema registry, it's got to be in that format, and that's how we know to look for it, right? So when I say, describe demo that inventory that exists, we'll use that schema in schema registry. Otherwise, we consider it not found for there. And then, of course, you can query the data. Right now, we're going and we're finding the schema, and we're reading the event data from Pravega, right? So at this point, we've I think there was 10 segments, right? So this probably was 10 splits that were created. And it's getting the data for each of these, right? And then, as you might imagine, since it's SQL, right? I mean, you can, whoops. Right, so, and you can query it and you can get as complex as you want with that. So that's just a quick example of Pravega, and of course, which is, I think, great on its own. And then, the real power comes in is you can join tables from, disparate data sources, right? You can use ECS and S3, object scale, S3, HDFS, MySQL, anything out there, right? So that's when you can combine all the different data sources together into single queries, which is like where the real power sort of comes in. Yeah, so I guess with that, I would leave it up to ask any questions. Open the floor.
I have a question. When we have a lot of data in Pravega, what kind of latency can we expect for a query like you just showed, like select star where sensor equals sensor 6?
Yeah. So okay, so that's a good question. So I think there's so I guess the answer is right now we're going to end up reading the entire stream, right? Which may be a lot of data, right? As you suggest. So if that's many gigabytes, we're going to end up reading all that data. What's certainly possible, but we don't have, is being able to use something in the where clause that will then help us narrow down where in the stream we need to look, right? So I mean, if you were able to just search between a specific stream cut, right, then that's where you would look. That's where you would look for that data. But right now we're looking at the entire stream, which could obviously take a while if it's large.
Are there any plans to do that where clause push down?
Yeah, those are all things that we're interested in going in, and haven't gotten there yet, but yeah, absolutely. Yeah.
Are you also considering building an index or the ability to use an index or even a columnar table?
We don't have any specific plans, but I mean, that's absolutely stuff that we want to get into. Yeah. I mean, yeah, we don't have any specific things that we've looked at, but yeah. I mean, we know that this is the next sort of area. I mean, so the basic stuff here is there and works, right? And the next is to make it better for users, right? Which includes making more performant, things like that.
Yeah. Well, and this is great for a lot of use cases. For an analytics use case where you do want to query everything. I'm just looking at could we go beyond this use case to more like a low latency business intelligence ad hoc query use case.
Yeah. They're
Claudio,
all things we're interested in, but yeah.
Claudio, when you say when you mention columnar format, so what is it that you have in mind exactly? Because when I think of columnar, I'm thinking about formats that store data in that way. Is that what you're referring to?
Yeah. So right now, events in Pravega are the row format, right? If you have 10 columns, there are going to be 10 columns on disk, and then the next 10 columns, the next 10 columns. So that's row format. So a column format will store them differently. It'll store them as the first column. It's going to be for all the rows. It's going to be contiguous, and then the second column for all rows will be contiguous. So the columnar format is used for like a data warehouse where you want to quickly scan just a few columns of your table, not all the columns. So I don't know how that would even make sense with Pravega streams.
I see. Sure. Okay. So you are referring to the format in which you're storing the data.
Yeah. Exactly.
Yeah. Okay. Got it.
Yeah, and just so I mean, Presto works in blocks and columnar, right? So there's if you look at the Hadoop connector, there's support for Parquet, right, which is also right, and yeah, that implementation there is obviously very different, right? I mean, most everything is row based, and Presto converts it to blocks, right? And Parquet is already that way. So it's the implementation there is much different.
Yep, and it's also worth mentioning that there is another S3 connector for Presto, which does have support for Parquet columnar data type. So yeah.
Yeah. Thank you.
What was that mention of an S3 connector?
So we've also, okay, so right now, if you can use the Hadoop, I don't know what the name is. It's either Hive or Hadoop connector. I'm not sure, but I mean they're sort of one and the same with respect to the plugin. So you can query objects in S3 using that connector, right? So you can have objects there, and you can set that up, and then S3 is another data source. But that if you want to use that involves bringing in like all the stuff that comes in with Hive and Hadoop, right? So setting up meta stores, and you have to bring in that sort of whole ecosystem and stuff like that, right? So we had also started working on, and not open source at the moment, but just a connector with just pure S3. So kind of getting at the heart of S3 and making it more lightweight. So you don't need to bring in all the Hive stuff.
And I guess you mentioned Parquet. I don't know about storing Parquet on Pravega streams, but maybe like you could store Arrow or Seabor or other formats on Pravega streams. It looked like serialization right now is coming from schema registry, so formats supported by schema registry are supported. Is that?
Yeah, right now we have those JSON protobuf and Avro, right? And that's because schema registry has native support for them. And then CSV, we have support for CSV. There can be others, right? It's just a matter of implementing it. And then if schema registry were to, then we would follow soon thereafter for those formats as well. I know schema registry has custom, ability to store custom schemas for custom formats. But the native ones for sure.
Yeah, cool. All right, so pretty straightforward there, I guess. Extend formats in schema registry and extend them in this connector.
Anything else?
I guess I had one more question, like how are you guys thinking about this, like stream cuts versus splits problem currently? It sounded like you're kind of ongoing with actually solving the.
I think we know what we want to do. We just need to get it done. I think we're in a position now to start going more after those optimization type things, right? I think the first stage was getting things stable and getting things running and working, right? And then building some things around it. And now I think we're at the point where we're going to get more into optimization. So I think we have ideas. I mean, there's already POC PRs out there for doing that. So it's just a matter of finishing those up and getting them in. But you know, I think we mentioned the ability to sort of define like an arbitrary size in megabytes or whatever to for your split. So I mean, we know how to do that. So just a matter of getting it all in there.
I guess I was curious. You're starting with a user provided list of stream cuts, but maybe that's just maybe that was just an easy way forward. I wondered if there were complexities around choosing the stream cuts, but they can maybe be arbitrary.
Yeah, I mean, I think that was more born out of you know, initially there's so I mean there's benchmarking things out there like TPC, I forget the exact name, so forgive me, TPCH. So it's more of a compare and contrast with Hive, right? So Hive all over S3 and Hive, you know, querying Hadoop and seeing how you know, querying the same data set, you know, between the two data sources, how they compared, right? To see if we were close. So that stuff came out of there, right? Because like in Hive, for example, right, they use 64 megabyte splits. That's what they write. That is optimal for them, right? So it was more to sort of be able for us to kind of mimic that size and have comparable number of workers running and things like that.
And maybe what about like Presto or Trino operators for Kubernetes? Are there things open source there, or is that where
we have? Yeah, so one of the things also that we've spent time on is an operator for Presto, and they will be open source soon. We, meaning Dell, we have approval from Dell to open source it. So I mean, I think that will be coming soon. So in Presto, I think when we started it, I don't think there was any real operators out there. I think I think now there's one, but I don't think it has any traction. I mean, of course, I could be missing some, but I don't think there's like a standard operator. And I know Presto, they've been looking for that. So we will have one. On the Trino side, there's I don't believe there's one that's free and open. I could be misspeaking, but there's Starburst Data, which is a commercial offering of Trino, and they certainly have one. And if you go with the commercial offering, then you get that. I don't think it's open though.
Okay, well, that's exciting news that we'll be releasing something. I hadn't heard that till now, so great news. I have seen, I think, charts on the Trino side, but maybe not a full-blown operator.
Yeah.
Cool.
Any other questions from the audience? Okay, sounds good. Thanks a lot, Andy. Karan.
All right, thanks everybody. And yeah,
Thank
let
you.
us know if you have any questions or anything. Yeah.
Hey, thank you.
All right, thanks all. Bye.